Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on zeros, singularities and poles. Lecture number 5, in which I will prove some remaining theorems. Now we prove the theorem 3. Statement of the theorem is: let the function fz be analytic in an open domain D and phi z be defined by phi z equal to 1 by fz, where fz not equal to 0, then f has a 0 of order m at a point z0 in D if and only if phi has a pole of order m at z0. Now we prove this. If part. Given that fz be analytic in an open domain D and phi z equal to 1 by fz, fz not equal to 0. Now let phi z has a pole of order m at z equal to z0. Therefore, by previous theorem, we get phi z equal to another function psi z by z minus z0 whole to the power m. Psi z is analytic at z equal to z0 and psi z not equal to 0. Implies that phi z equal to 1 by fz, 1 by fz equal to psi z by z minus z0 whole to the power m, implies that fz equal to z minus z0 whole to the power m psi z. Let this is number 1, this is number 2, this is number 3. Since psi z is analytic at z equal to z0 and psi z0 not equal to 0, therefore 1 by psi z is analytic. Therefore, from 3 we get that fz has a 0 of order m at z equal to z0. Here fz equal to 0 if z equal to z0, that is z equal to z0 is the 0 of fz and as here power is m, z minus z naught whole to the power m. So z naught be the 0 of fz of order m. Proved. The only if part. Let fz has a 0 of order m at z equal to z naught. Therefore fz equal to z minus z naught whole to the power m, another function eta z, where eta z is analytic at z equal to z naught and eta z naught not equal to 0, implies that 1 by eta z is analytic. Let this is number 4. From 4 we get 1 by eta z equal to fz by z minus z naught whole to the power m. Let this is number 5. Since 1 by eta z is analytic, therefore 1 by eta z equal to a naught plus a1 z minus z naught plus a2 z minus z naught whole square plus dot 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 plus a minus 1 z minus z naught whole to the power a minus 1 plus am z minus z naught whole to the power m plus dot 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 dot, implies that 1 by eta z z minus z naught whole to the power m equal to a naught by z minus z naught whole to the power m plus a1 by z minus z naught whole to the power m minus 1 plus dot 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 am minus 1 z minus z naught plus am plus sigma n equal to 1 to infinity a m plus n z minus z naught whole to the power n. Let this is number 6. Using 4 we get 1 by fz equal to a naught by z minus z naught whole to the power m plus a1 by z minus z naught whole to the power m minus 1 plus dot 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 plus am minus 1 by z minus z naught plus am plus sigma n equal to 1 to infinity am plus n z minus z naught whole to the power n implies that 1 by fz is phi z equal to a naught by z minus z naught whole to the power m plus a1 by z minus z naught whole to the power m minus 1 plus dot 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 plus a m minus 1 z minus z naught plus am plus sigma n equal to 1 to infinity a m plus n z minus z naught whole to the power n. Let this is 7. We see that right side of 7 is in the form of Lorentz expansion, in which number of terms in principal part equal to m. Here in principal part we see that am plus am minus 1 by z minus z naught plus dot 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 up to a naught by z minus z naught to the power m. Here we see that maximum power of z minus z naught in denominator is m. Therefore phi z has a pole of order m at z equal to z naught. Proved. Now we prove theorem number 4. Statement of this theorem is, let z naught be a pole of fz, then there exists a neighborhood of z naught which contains no other poles of fz, that is, poles are isolated. Given that z0 be a pole of fz, let fz not equal to 0 and phi z equal to 1 by fz. We know that if fz has a pole of order m at z equal to z naught, then phi z has a 0 of order m at z equal to z naught. We know that zeros are isolated. Therefore, zeros of phi z are isolated. That is, zeros of 1 by fz are isolated, implies that poles of fz are isolated. Proved. In another way, we may prove this. Given that Z0 be a pole of function of Z, therefore we may expand fz in Laurent series in the deleted neighborhood modulus of z minus z naught is greater than 0, less than r, as follow. Fz equal to sigma n equal to 0 to infinity an z minus z naught whole to the power n plus sigma n equal to 1 to m finite number of terms in principal part bn z minus z naught to the power minus n. Here we see that z naught is only one pole of order m in the neighborhood of z equal to z naught. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.